Advanced apologies for the background noises. A box contains two $5 bills, five $10 bills, and one $20 bill. Construct a probability distribution for the random variable x, such that x is the number of $20 bills after a bill is randomly selected and replaced 3 times. Whew, okay. All right, so this doesn't help us necessarily. These are independent events. So it's not like choosing one bill eliminates the rest of the possibilities for all the bills. So we just want to be really careful about this. So this is a 3 possibility sort of situation. You can either grab a $5 bill randomly, you can grab a $10 bill randomly, or you can grab a $20 bill randomly. And if we think about these probabilities, the probability of pulling a $5 bill is going to be 2 out of 2, 5, 6, 7, 8. So a quarter chance you're going to get a $5 bill. A $10 bill, 5, 6, 7, 8, 5 out of 8 chance you're going to get a $10 bill, and a 1 out of 8 chance. So 2 out of 8, 5 out of 8, 1 out of 8, 2, 7, 8 out of 8. You want to make sure that these all add up to 100%. Okay. Well, what can happen after that? Oh my. Okay, so you can either pull a $5 bill again, a $10 bill again, or a $20, or a $5 bill again, a $10 bill after the 5, or a $20 bill after the 5. Same thing here. You can pull a 10, then a 5, a 10, then a 10, and then a 10, then a 20. And then the last thing, again, 20, then a 5, 20, then a 10, 20, then a 20. Okay, but we're doing it 3 times. So, because I'm evil, you can pull a 5, then a 5, then a 5, a 5, then a 5, then a 10, a 5, then a 5, then a 20. Yeesh. Then you can do a 5, 10, 20. And I'm doing this because I'm showing you that this is the process, right? So this is the process regardless of how small or large your sample size is, sample space is. 5, 10, 20. I'm doing this for you. 5, 10, 20. Yikes, 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 yikes. So what did we get ourselves into here? 5, 10, 20. I'm just going to start making a list, right? I really am. Right? But this is required, you know? Like, this is part of the process. Okay? So we can either we could pick a 5, 5, then a 5, a 5, 5, 10, 5, 5, 20. We could do a 5, 10, 5, 5, 10, 10, 5, 10, 20, 5, 20, 5, 5, 20, 10, 20, 20. Systematic. And we know we have 27, right? And there's ways around this. But if you want to guarantee you have everything, then you can list them all out. Okay, so this is pulling a 5 first, so then we could also do a 10, and a 5, and a 5, a 10, a 5, and a 10, a 10, a 5, and a 20. 10, 10, 5, 10, 10, 10, 10, 10, 20. 10, 20, 5, 10, 20, 10, 10, 20, 20. right? As long as you take a systematic approach, then you can do this however. So you pull a 20 first, then a 5, then a 5, a 20, a 5, and a 10, 25, and a 20, a 20, a 10, and a 5, 20, 10, 10, 20, 10, 20. Ooh. 20, 25, 20, 20, 10, 20, 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 27 things can happen. So it says the number of $20 bills. Okay, so you're going to say, all right, well, no, just kidding. A random variable X can either be 0 $20 bills, 1 $20 bill, or 2 $20 bills. Actually, or 3 $20 bills, because you could pull a 20, 20, and then a 20. And then you just figure this out, right? So, okay, well, X, probability of X, 0, 1, 2, 3. So make yourself a chart. It's a little bit easier to organize. And we know that there are 27. Okay, 27 outcomes. All right. So let's count all the ones where there are no $20 bills. 1, 2, 3, 4, 5. Oops. 6, 7, 8. All right, the conversation we need to have is, are we counting? Yeah, here we go. Are we counting something like this to be the same as this? And we're going to say no, because if these things were happening, they selecting it and replacing it 3 times, we're going to count those as separate. This is like bill 1, bill 2, bill 3. Bill 1, bill 2, bill 3. We're going to count them separate. Someone might argue with you on that, but that's not a big deal. So 1, 2, 3, 4, 5, 6, 7, 8. So 8. 27. Okay. And then we're going to look at one $20 bill appearing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Looks like 12. So 12 out of 27 can be reduced though, which is 4. Okay. 4 out of 9. I'm just going to divide both by 3. I don't know why that's happening. Okay, and then let's focus on 2 $20 bills. 20, there's 2, 3, 4, 5, 6. 6 out of 27, which is 2 out of 9. And then 3 $20 bills is just a 1 out of 27. But I like this because you can count these up, right? So you have 8 out of 27. We want to double check these add up to 100%. So 8 plus 12 is 20, plus 6 is 26, plus 1 is 27. So we just want to make sure they add up to 100%. All right, so then this table would be what you graph. So let's take a look at that right down here. And it might be easier to do this in decimal form. I think it's easier for me to do it in decimal form personally. 8 divided by 27, 296. This is 44 repeating. This is 22 repeating. I didn't mean to do that. 4, 2. And then 1 out of 27 is 0.03 something. Yeah. Oops. 0.037. All right, so we want to make sure we remember that we are making this graph. All probabilities have to be between 0 and 1. And my highest value is 4. I might actually just do like 1, 2, 3, 4, 5, 6. Not that that matters, but yeah, I might do that. All right, so I'll do 0.1, 0.2, 0.3, 0.4. I'll just do that. Okay. So probability is 0, 1, 2, 3. So probability of getting no $20 bill is 0.296, which is very, very close to 0.3. Go ahead and just do that. 1 is 0.44 repeating, so this is 0.45. We'll do like a little something like that. And then 0.2 repeating, something like this. And then 3 is 0.037, which is just nuts because this is 0.5. I mean, just kidding, this is 0.05. So 0.05, just a little bit lower than that. Right? Skewed right. Probability distribution of X. And then this is probability of X. This is number of, I don't know what's going on. $20 bills. I'm sure it's just like a technology issue or something. There we go. And that's how we do it. That's a tough one, but that's how we do it.